last but not least, Tilman from ETH. That's the final talk of the workshop.
Okay, let's see how that works. Okay, so it seems to work. Thank you very much for organizing the workshop. So I think it may be a big applause for the organizers. Such a great job and such a fantastic title of the workshop. We will all remember it. I mean, you know, we go to many conferences over the years, but I'm pretty sure we will remember this one. Let me maybe first zoom out a little bit. In terms of what humanity, one of the inventions of humanity was, of course, the wheel. I mean, at some point, people were fed up with just taking the stones or something and then handing it over to the next person and so on. And they came up with, well, they started off with rollers and so on. It took a while, and then wheels, and nowadays we are, of course, very sophisticated. We are also live, I mean, in times with their own challenges, and our challenge is now not to transport classical cargo, but to transport quantum cargo. I mean, that's also what we want to do in the cavities, in lots of systems. We want to find ways how we can connect and transport quantum information or quantum states. And in my talk, one point will be a system where we produce singlets and then use a topological pump to pump them apart, and we can pump them far apart, and then we can move them back into their initial orbital. So you could imagine it's like if you have paired electrons in one of the molecules, and we're able to take that entangled state to move out those two electrons and still have entangled pairs, but that requires that you can put them back in. And this is a journey which goes from surprises over topology and then a natural scaling. So we started off, or it all started off that we listened to our experiment, a cavity experiment, and we kind of learned from a quantum simulator something about fields, which we could have come up before, but we hadn't. And then about topology and in the presence of interactions and without heating. And then a scaling up of a high fidelity swap gate, so very high fidelity. So it's 99.91%, and it's an average over 17,000 gates. So there are two concepts I would like to briefly remind you of. One is the topological pumping. So an easy way to implement is you take a static lattice with a certain period lambda, and then you take a second lattice with twice the period. You move it relative to the first lattice, and this time and space periodic potential allows you to transport, for example, insulating states or localized Wannier states. Now you may say, okay, well, let's first look at this, and then then I'll come back to what you might say. Okay, so one way to look at it is you look at, this is the black curve is the added, there's some potential, and let's start up in the top corner. There the atom, or it's a one-year function, which is sitting on a dimerized level, and then this dimerized level gets into less dimerized in a single one, and so forth. And we can see that that state adiabatically, I have something here, no. Moves. Is that working? And then it's this one, yeah. It moves here over a cycle, over half a cycle period, moves again to a shifted by half a lambda shifted position. And now you might say, okay, that I can just take a long wavelength lattice and move that. What's the point of the whole thing? The non-triviality in this is actually that there are two mini-bands, so this long wavelength potential splits the short wavelength potential in two bands, and one lower mini-band and an upper mini-band, and they move in opposite directions. They have different Chern numbers, and the particles move in opposite direction. You can guess that's, of course, what we do with these singlets, that we move them in different directions. Then I would like to give a second concept, but that had already to be been introduced. Let me give a slightly different view on it. So if you take a Bose-Einstein condensate in a cavity, the way you could think about it is, since we are very far detuned, many nanometers, you can look at it as a superfluid refractive index. So you shine light, or in this case a standing wave, on this superfluid inside a cavity, and now you wonder what will happen. And then first at low intensities, yeah, well, we would say, yeah, it scatters, but of course it scatters like a piece of glass, and it will go, the light will go through. However, it is a superfluid, or it is a fluid, some type of fluid. And now you can imagine if there was a density wave in this fluid in a direction such that you get Bragg scattering, then I could scatter actually into the cavity. And now you see it is a competition between, for the energy of the system, that it is in a delocalized state, momentum zero state, where it doesn't have a density wave, or it needs to come up with the energy to form a density wave that can scatter. And this energy, on the other hand, comes from the potential that is formed in the cavity. So it is a competition between zero-point motion and the potential that is formed in the cavity. And you get this phase transition, which you can map to the decay transition, and which breaks, for this implementation, it breaks as a Z2 symmetry. And the way how we detect it is, on the one hand, the momentum pattern of the atoms, and then on the other hand, it is the light field coming out of the cavity, where we can also measure the phase relative to the pump beam. And then you've seen that. So if you turn your head around a bit, then you remember. And what is plotted here is the pump strength, increased pump power, and here the detuning relative to the cavity. And you see, the more I detune, the more I need to drive my system to get into this self-organized phase. And now these are ready tuned. So that means if you create a field, I lower the energy in potential for my atoms. So that makes a lot of sense. If I can lower it, then I gain energy and I can put it into the ripple. And now we change the arrangement a little bit. We have a cavity, we drive it under an angle, not perfectly back reflected, and it's indicated here blue, we blue detune it relative to the atomic transition. And now one can think, what can happen? Because if I blue detune, if I build a field up, then one could argue, that's no good because I just increase my potential, so I cannot gain energy. But then you think a bit more, then you realize, if there is already a field, then I can, if I have destructively in the field, I can actually lower it. So it's not a totally hopeless case. But it's not only hopeless, but it also has some intriguing aspects. And one intriguing aspect was that we saw a signal like this. So we changed the power in this system, and then we measured the phase between the pump field and what's coming out of the cavity, and it went into this type of steps. When people showed me, when my coworkers showed me this data, I said, oh, it looks like jokingly, of course, it looks like a quantum Hall effect. Of course, at that time, we did not know what it is, but I will tell you. But let's first introduce a quantum simulator where we made this experiment. That's a closed system. That is the open system. And that is what you might be interested in. that is the cavities. So the pump beam comes from here. And so we have all the 60-degree angles. In the experiments that I will show you, we'll use only one cavity. But there are many things one can do with several cavities. And the speciality of those cavities are that they are this usual super high reflecting mirrors, but milled down to here to 600 micrometer width, and that did work. And this is a collaboration with Tobias Donner and the impact team. And here you can see them in their lab and the recent PhD of Alexander Baumgartner. Okay, so what was the first thing we saw? Already with this experiment, the first thing was for us puzzling. We set up this experiment and changed the knobs. And then we saw this data, again, pump power against cavity detuning. This here, this phase, crystal 1, that was what our intuition was. So our intuition was, as long as the atoms are delocalized and not in the minima of the blue detuned pump, because if the pump is very strong, then they are in the minima of the blue detuned, and then there's no scattering possible. And but if the pump is weak enough, then they are also in the maxima or over the maxima. My wave function is just a bit modulated. And then I can, if the atoms scatter at the positions of the maxima and with the right phase, they can lower the potential energy. And we would expect, if we increase our pump power and localizing the atoms more and more, then this phase vanishes. And that's exactly what this dark region shows. And we were happy. But then we kind of were not totally happy. We were a bit uncomfortable with the data because there was some light coming out of the cavity at in a different region where we did not expect. So we teamed up with our theory friends, Nigel Cooper. And at some point we got the email, is it possible that you don't have a perfectly retroreflecting pump lattice? And we thought, yeah, yes, of course, no, it's not perfect. And that, and that actually explained this second phase. And we could measure, meanwhile, we had measured that it is a phase in that sense that their stable light field is coming out of the cavity with a certain relative phase, with a certain fixed phase. So you scatter in, you get a phase out. And that phase is different from by 90 degrees from the other crystal. So they couple to different quadratures of the light field. And the reasoning why the imbalance gives us a scattering, that is quite simple. Now imagine you have a strong blue detuned standing wave, then the atoms are localized in the minima of the potential. But now there is the rest component of the not perfect back reflection that will scatter from the atoms. And in that one, they can then create a potential that lowers their energy. So they scatter from a potential which is shifted in space by lambda half, by one period or a quarter of a period. I mean, depending on where your crystal sits, you will see another phase coming out of your cavity, because you scatter light in the end, and you can think of it as shifting your refractive index pattern in space. And actually, those two crystals, they have a different center of inversion symmetry. So there we were quite happy. And then we looked at what is happening between those two orders. And there we saw that there a first on order phase transition is happening, and we could go from one phase to the other, and we could see kind of a ringing, and then it would go into the second phase shifted here by pi half, coupling to the other quadrature of the cavity. That was for a situation where we had very small cavity decay, so far detuned. And when we went to the situation where we had larger kappa, so the cavity, well, more leaky cavity, then we saw kind of these pictures which did not look so nice. But fortunately, we did not just disregard them because they don't look nice. Because what they really show is the steps in the phase. So we then looked at this data, and we could see that as we increase, so on this axis, we increase the power, we see that the phase is always continuously moving, and that at some point it is locking into another phase, and it is always by full number plus a half, so it's n plus 1/2 pi. And well, we went through different regions of detuning. It's always the same type of behavior. And we could, yeah, one can plot it in such a diagram here so that's in the quadrature diagram at different times. And so you get a winding over time of this phase of the cavity field. Then the question, of course, was where does that come from? And if you look at the light field, because I mean, we have all the information about the light field. So in the end, it's an interference pattern in the cavity. And you can then, well, you can plot it, and then you can change the phase of the cavity. And then what you see is you have two components in your light field: a static short wavelength lattice plus a double wavelength lattice, which is actually moving. And that is exactly a kind of the topological pumping situation. So you have one piece static and the other one is moving. And in a way, let me try this view on it. You have an imbalance here, and you have some dissipation. What does that mean with the dissipation out of the cavity? That means if you get more photons from here into your sample and dissipate out in that direction, you get effectively a light pressure. So you push on the system. But it is in a periodic potential. So you get the consequences that you get Bloch oscillations. And the system has difficulties how to take the momentum. What it does, it moves sideways in this periodic fashion. And from that, here we can see what the potential then looks like. It is exactly what is in a topological pump. And we could also see in our experiment that the center of mass of the cloud moved with the number of cycles of the phase winding. And it is a very special topological pump in the sense that here it is the dissipation that drives this pumping mechanism. So it's not from outside, but through the dissipation it is moved. And one other way one can also look at it, there are these two competing phases, and they both get soft. And then you get a coalescence where you have one gain mode and one damp mode, and this mode is then oscillating. Okay, so, but what we also realized then is, well, if that is working nicely and you can get a topological pump, then in principle, I thought that that should also be possible in our lattice experiment. Because with topological pumps, it was always difficult to take a green laser beam and say 532 and 1064, and then the relative positioning, the refractive index changes with the temperature, pressure, and everything, and it's getting very difficult. But before I show you how we implemented this topological pump in our lattice experiment, I would like to briefly show you another simple, conceptually simple experiment with a cavity. And here is the cavity. It's on a piezo. It's super polished mirrors, and the piezo has holes such that one can also create a three-dimensional lattice in it. But for the experiments I show you now, it is the simplest configuration. You have your BC and you pump it just with one laser beam. Yet the polarization such that you drive orientation changing vectorial transitions. And now you can imagine, so we prepare that in the MF equal 0 state, the BC. And then you excite, so that is 10 nanometers or more off resonance. So we have the tune out wavelengths between D1 and D2 line. And then, well, the first process you think of is, okay, so there is these are magnetic sublevels, MF equals 0, say MF equals +1. If your cavity, that is a cavity resonance, a white thing, then you would get you would get super radiance in this state, very similar to Wolfgang's and Dan's experiment quite some time ago. Now, one can ask the question, what is happening if I tune now the cavity away? Then this process gets off resonant. And then the system, well, is looking for the next process that it can do. And that is now to take this virtual photon, this collective super radiance photon, and then scatter back into the pump. If that process is resonant, then it can, of course, overcome the lower order detuned process. And this, this means, so the first photon will be absorbed from the pump beam and scattered into the cavity. The second one takes from the cavity and scatters into the pump beam. And as long as you don't lose any photon out of the cavity, it's a completely coherent process. And this process, there is a strong analogy, which I don't 100% understand, with James Thomson's work. But yeah, it's pumped in different directions. There are some differences, but I think conceptually there's a lot similar. And here we estimated that in our experimental parameters, we create 10 pairs per photon loss. And and then we looked at this process experimentally. We did actually see, yes, all the MF equal +1 are scattered forward, the -1 backwards, and it has a characteristic where when we increase the atom number, that process suddenly gets critical. And there's a lot of analogy to nonlinear photonics, and also the situation that you can have a single or two channels. So the two-channel situation is the following. If we look at this diagram, and Monica will also know this diagram because her process is in space. That's actually where we kind of came to the idea to try that. Our process is where you have localized traps, and our situation is, in a way, a momentum space situation. So these are our atoms in the BEC. And now we can go through two paths. We can go through the path MF, first photon is MF equal plus, or the first one is MF equal -1. They totally have to add up, but that both are flipped. And now by cavity detuning, we can, if we detune very far away, then the relative detunings are almost similar, and then you can go through both channels. That's the wrong one. And that's on the right upper corner. And then, of course, we wanted to measure what are exactly the correlations. It should be number squeeze. I can already tell you that we are improving our imaging, which else we have not yet seen it. We have improved it, so we will measure soon. But we can see the following. We can see another statistical effect that we just count the distribution of the number of pairs that we see in a given situation. And there we see a Bose-Einstein contribution. And if we do that, compare that with a truncated Wigner, there we see that we also expect a Bose-Einstein distribution. And if we put a seed photon, one seed photon in the cavity, then the distribution already looks considerably different. So from that, we conclude probably it's driven by quantum fluctuations, so that it comes up, that it scatters at the first time at all. And that is what the lab looks like. And actually, I only at that point, I wanted to show you the cavity, but now it's twice, but it's fine. It's a nice cavity. Okay, let me now come to another topic at my heart, that is quantum gases in optical lattices, in this case, fermionic potassium gas, putting it into an optical lattice. And then you get atoms almost one per side, but holes also, but you can also prepare, since we have two spin components, two per side, and we can make them attractively interact. And there you have your spin singlets per side. And the whole system is, of course, can be described as a Fermi-Hubbard model. So the atoms are tunneling on this lattice. And then if two particles are on the same side, there's an interaction energy, U. And we will put this system into a topological pump, and where we can then also change the interaction. And that physics I will show you now. And that's a view of the experiment. And I'll give you an insider view. So again, it looks like a typical atomic physics experiment. And most importantly, the team, this team is led by senior postdoc Konrad Fiban, and latest PhD who finished his PhD is Gia, and he contributed, as the others, also very much to the work. I should tell you one other thing. The way we read out is spectroscopically. So what we do is we use radio frequency spectroscopy to transfer and use the controllable interaction energy. So if there's, so I have here sides green, only one of the spins, they are red and green. And here are sides with two spins. And now we can switch on interactions. And then use a radio frequency to do the spin flip. And there we can decide, do we spin flip this or that? And we spin flip, and then we measure by Stern-Gerlach separation the number of atoms we have in the different spins. So that gives us information on these singlets. Okay, and then the scheme we realize to get the topological pump. The nice thing about it was that we just had to rotate by a tiny bit one of our polarization optics in the standing wave, and then one gets a potential. Well, this here, that was my first little Mathematica, so that's why it's wobbly. But the idea of the whole thing is that you have a set of laser beams where you have 80 megahertz different in frequency, and that gives you a square lattice, as is shown here, just two standing waves. And then there is a second laser beam from the side, which is almost the same frequency as this one, just a tiny delta. You first forget that it's assumed same frequency. And then you interfere those two beams, and then you get a checkerboard pattern. And you can also imagine now, if I change a little bit this frequency or wind the phase, then my bigger checkerboard my checkerboard pattern will move. And it is such that, okay, we have a back reflection, but it's totally, if you have a 10% or so stronger movement of the one pattern relative to the other, then you get a perfectly fine potential for the topological pump. And here's another way how one can imagine that in our topological pump kind of tubes that's shown there. And it was one of the experiments. I mean, sometimes you do experiments super complicated. You try and half a year, more than half a year, and so on. Here it was almost immediately that it worked. We could immediately see that it is pumping. So there are the atoms in the lowest miniband, a little bit, a few atoms were in the higher miniband. So they moved in the other direction. And then we thought, what can we do what other people hadn't done? And there our particular point that we had tunable interactions. So we looked at how robust is a topological pump against interactions, and that's there on the right-hand side, and we see for attractive, and then up until an interaction of U equals delta equals 2 delta, that's the offset, the relative offset between the two sides. There we saw that the pumping breaks down. And and another question we asked, I thought, okay, so we have this fantastic topological pumping, so it works, it pumps far away, and then at some point you wonder, what is actually happening when you have a trap potential, but what will happen there? And what we saw there was that it's pumping until it comes to a point where it is reflected back. So what you see here, some atoms are lingering on and then finally are reflected back. And if you analyze it, there are churn markers there. One can see that the churn marker, which gives you is 1 if you have a churn band with 1, that it goes down. And you can also look at it that you have at the point where your lattice, your delta with which you modulate, if that is the same as your gradient induced difference between the sides, that is a point where you have this turnaround and couple the lowest miniband to the upper miniband, and where beyond that you have a topologically trivial system. And here, compared to the flow case systems, the nice thing is here you don't have heating. It's all, the energy scales are all this miniband energy, and you don't put anything in higher band where they can tunnel fast and dephase. We then did the same experiment with interactions, and then we saw that there is something scattered backwards earlier. So here you see the pump, but here you see an earlier reflection, an interaction-induced reflection. So kind of your boundary of topologic to non-topological is shifted due to the interactions. And that one can also imagine, because you have this energy offset, and as long as your offset doesn't go through 0, either the offset and both, of course, the relative tunneling shouldn't go through 0, but if one goes through 0, then you go into the topologically trivial situation. And here, what is happening here, that the energy U adds to the trapping, to the gradient of the trap. And then what you get is that one particle is pumped further and one particle is reflected back. If you had 2 different spin states. Then we analyzed that in a simulation, and then we saw, these 2 particles at this barrier, they are correlated. They are Bell states, which are moving apart. Then we thought, let's do an experiment where we can see these correlations. And that will come in a moment. Here it's just that, or if we just pump all the pairs, can also do the pairs, let them pump, and that is done with a very high fidelity. I think here it's 99.5%. Okay, but let's go to how we can look at the singlets and how we do singlet splitting in our in this topological pump. So with our reduced reflectivity but the more complicated thing is the two lattices that we have, we can form all sorts of potentials, and in particular this, in one direction, this double well potential, which we can control the double wells, the offset and the tunneling. And let's look at a single of this double well. And let's assume we have attractive interactions and the singlet, which is produced by cooling in the end, in our initial cooling, that produces a singlet with attractive interactions. And then we can change the interaction and the relative tunneling. And so we go to repulsive interaction and then open this channel through the barrier. And then we get a Heisenberg singlet, a symmetric Heisenberg singlet on those two sides. That's how we prepare. And that state, since I don't know where the green, or whether the green is left or the green is right, it is a correlated bell pair. And then we thought, can we now move this bell pair apart with the topological pump? Because one of them is in the lowest mini band and one is in the upper mini band. And that is the idea of bringing it apart. So often people say, the entanglement that you have in singlet state, singlet electrons, localized fermions on the same orbital is useless. But of course, if you take them apart, then it becomes useful. And here's again the picture of the topological pump. It's characterized by the lattice offset delta and the relative tunneling T and T prime. And you get the topological pump if your relative tunneling and your offset are moving on a circle enclosing the zero. And so the first thing that we do is, so we split it, and now we want to know, did we do everything coherently? Does everything, do we really have a singlet state? And that we can do by applying a magnetic field gradient, and then we get singlet triplet oscillations. And now, depending on how long we let it oscillate, we should go back into a singlet, or in the triplet, or singlet triplet. And so we can measure those singlet triplet oscillations. That is how we extract our information on those pairs. Yeah, it goes back, and then we do our spectroscopy. And now we do the pumping apart, and then do singlet triplet oscillations over these long distances. And then we pump it back and check whether we have still singlets or whether we see those, whether we can make our oscillations. And here we see now that for the same magnetic field gradient, we have much faster oscillations, which makes sense because kind of the singlet and triplet are in a decoherence-free subspace, which can be broken by a magnetic field gradient. Of course, if I go further apart by a given magnetic field gradient, I will see faster oscillations. Now you might say, okay, but I said I have a lot of filled sites. I mean, our first data showed all sorts of frequency for the singlet triplet oscillation, because then we did not understand the experiment, but then we had to think. And then, of course, the problem is you move those singlets apart, and then there's another singlet, from another singlet, an atom coming. So then what you want to do is a swap gate. And then you want to swap them through each other and then backwards. And that's also that's exactly what we do. Each time, or all the gates, when we take them apart, is all tuned such that we have swap gates. So we have a super exchange interaction, we swap, and then it moves further, and then we can move back. So that's why kind of one can look at it as an intertwined entanglement. And we can also reflect it by having a swap square. Yeah, okay, that's what was the initial animation. That's exactly what's happening. And we can also do variable swap gates by changing the super exchange interaction and reflections, and we see then, well, we swap square gates, and we see then the characteristic frequencies in singlet triplet oscillation. And then, of course, one starts to dream, couldn't we do that in different directions? Yes, we can, and we can move the atoms and maybe kind of locally blocking, and with a tweezer, and then you get a reflection, and you, of course, you can build a quantum computer. And but then you wonder, how good are actually our qubit gates? And there we made progress. Our qubit gate, our gates, at least the swap gate, is really extremely good, and we can realize purely geometric 2-qubit swap gates. And the trick is there's no dynamic phase, so it's insensitive to lattice inhomogeneities, and we get with this system a loss-corrected fidelity of 99.91% across a system which has 17,000 atom pairs. And the basic idea is you go to interaction 0. So basically what you have is your atoms tunnel to the other side, and they have swapped. And this process is a very robust process. You can do that, of course, backwards, and you can do it back and forth and back and forth and back and forth, and check how stable, what is your singlet fraction. However, how can you measure that this is actually what is happening? And there, the nice thing is, if you have to look at the energy spectrum. So the state that we are looking at is not in the lowest mini band, but it is an excited state. It's the energy 0 state, or, well, we had it earlier in talk, it's a dark state with respect to our drives. And it's not only, well, that is one dark state. I can show you how it looks like. That is, we can rotate it from the initial singlet state, which is 1 up and 1 down. And then it goes through a state which has a double occupancy, that D is shown here. And that is what usually people for super exchange gates, they always wanted to avoid double occupancies, because I think in quantum dots that makes a lot of problems. Here it doesn't make a problem at all, in particular if you're non-interacting. And so, and there is, yeah, an important point is that there is another triplet state which doesn't acquire that phase. So if you have a symmetric singlet, spin symmetric singlet, if you change the positions, you get a minus sign. But you want to measure that minus sign, and that we can measure against the triplet state, which also has also flat energy. And well, there on the right-hand side is an illustration for how this dark state changes over the lattice position change. And the way we then measure is we take our singlet and then we prepare it in a superposition. We make a pi half pulse so that it's a superposition with a triplet state. And then we do our swap gate. And then we get a different sign. Okay. And we can do that now. And then we can do our singlet triplet oscillations. And now we see, so those two curves show here, the blue one is zero gate. So then we see this singlet fraction goes down. If we do the swap, and that reflects the minus sign, the singlet fraction goes up. So that's showing the relative phase. And then we did that a lot of times. And then we measured, now I'm getting nervous. So we measured that it's almost almost the last slide. And then we measured the fidelity, and then well, the raw data you see there over 32 times applying, and then we looked at a situation where we didn't apply any gates, and then we get that way. So there we had some loss, and that's the loss corrected gate. And then we did also, it should be due to the gap, it should be insensitive to noise. So we applied lattice noise, and then up to I think it was like 3 kilohertz or so width. So we could see if we increase the noise first, nothing is happening. After critical level, the fidelity goes down. One can also go into the regime of entangling gates. And there, of course, we need interaction. It's no longer purely geometric. And I thought there is some, okay, there's one thing missing. So this direct exchange gate is located here. That's our triplet state. That's splitting up those. Super exchange is up here, or here in this state. And the nice thing about this direct exchange gate, I think Trey Porto, he had realized that already 2007 or so, that they are cool, the direct exchange gates, because they go only with u, the phase you acquire, only with u times the time that you of your movement process, and that doesn't go in any lattice tunneling or stuff like that, which can make it very difficult. You need perfect lattices. And in our big ensemble and non-perfect experiment, we immediately got to this 98.3 fidelity for the swap gates. Okay, so we had a surprise. We tried to understand, that was during COVID. Then we came to conclusions and had fun with topology. And most recently, we had done these gates, and of course are curious where the limits will be. Thanks to all the teams. And yeah, now we can think of full control and so on. And I think in reply to Dan, this method of gates is compatible with cavities. And I would argue, and I come from I'm not working for Misha, and I come from a neutral country. I would argue that maybe one should rethink Rydberg gates and have different gates and integrate them smaller so that the energy scale is relatively higher, but keep the cavities. Thank you for your attention.
Thank you. In the work where you show there's spin orbit coupling through cavity polarization, is there a way you can suppress the other cavity mode that contains the unwanted polarization?
Sorry, okay, cavity experiment?
Yeah, the one where you showed you coupled the spin and the
okay.
mechanical modes of the atoms, right?
Okay, the scattering, the pair production.
Yeah, how do you control not scatter into other cavity polarization? Because I believe the cavity.
We are at the tune-out wavelengths, and we are that otherwise we have additional mechanical effects, so that we don't have, and those are the only resonant processes, and also with our polarization. So that's why we can. The only processes are the scattering in the vectorial process.
So there's no Rayleigh process. There's only Raman process.
Yeah.
So in this, I guess, new approach to quantum computing, is there a way of taking advantage of having fermions in a lattice? I mean, that's maybe one thing that is nice a good question.
We thought, of course, the quantum statistics comes in because the bosons would have other quantum statistics, so that will matter and change. Of course, it is extremely important to be able to tune to zero interactions. But I would not say a principle, it only works for fermions. In that sense, it's not a fermion, it's not there is this notion of fermionic quantum computer, but there you need to have control over, say they want to have half-filled modes, and you have to have, if one mode, you're unfortunately filled instead of not filled, you run into trouble. Here it is in the spin sector.
Okay. Wait, so let's thank Tilman again.